By definition, corrosion is the degradation of metal due to a reaction with its environment. In the metallic structure, we see that electrons are in free motion within the metal, hence are called free electrons. These free electrons, in fact, define the state of the metal. As soon as a fresh metal surface comes into contact with an environment, in our case a physiologic solution, two typical reactions take place. Oxygen molecules move to the surface of the metal, where they are reduced and liberate electrons. This is a cathodic reaction. This happens all over the surface where the few molecules of oxygen are available. These electrons will be transferred instantaneously to the metal atoms to form metal ions. This is an anodic reaction. An electrochemical corrosion reaction has occurred. This consists of an anodic and a cathodic partial reaction. On metals, the two partial reactions must not be physically in the same place. Electrons can be exchanged through the metal surface as an electric current. We can talk of a corrosion current which is proportional to the amount of corrosion, but we cannot measure it directly. In a corroding system, the anodes and the cathodes are short-circuited. When the process is repeated extensively, we see that cathodic and anodic reactions occur all over the surface. The metal dissolves, or in normal terminology, corrodes. Other products of the electrochemical reaction are possible, namely oxides and hydroxides. These can form either directly by reaction with oxygen or by reaction of the metal ions with a metal. Such reactions are necessary for passivation. Metal ions are produced, and by combining with oxygen, an oxide surface is slowly built up. Both the corrosion and passivation reactions can take place on any surface. On a passivating metal, the oxide formation dominates over the corrosion. We can state that even on fully passivated surfaces, there is a very small but finite corrosion reaction taking place. The passive film is said to be in dynamic equilibrium. On fully passivated stainless steel, due to the isolating properties of the passive layer, it is difficult for electrochemical reactions to occur. Overall reaction rate is very low. On any metal in an electrolyte, such as a physiological solution, we can measure the electrochemical potential, often called the corrosion potential. This indicates the state of the metal surface and can be easily measured. Passive surfaces have high corrosion potential. As soon as the layer is damaged, for example by micromotion between implants, a current is created and the resting potential drops to the so-called flayed potential. The cathodic reaction can occur once again all over the surface, but the anodic reaction is concentrated at the damaged point. If the film formation dominates, the metal may repassivate, and the corrosion potential will return to its original value from the low value typical of a rapidly corroding metal. The damaged site repassivates, and the potential is reset to its passive state. Charge transfer, and with it corrosion, is once again greatly reduced. The basic and very simplified anodic reaction is now displayed. This mainly forms a chromium oxide passive layer typical for stainless steel. The previous situation occurs under ideal conditions where enough oxygen is available locally to assist oxide formation on stainless steel. But of course, such situations are not common, especially when fretting occurs. Often, undesirable corrosion products can result. Going back to the surface defect, the cathodic reaction occurs where oxygen is available, Metal ions form at the anodic site, creating a charge transfer. The charge must be balanced where there is a large excess of positively charged metal ions at the damaged site. To do this, the fastest and most available moving anions in chloride solution are the chloride ions themselves, which are sucked into the embryo pit. This produces an even more concentrated metal chloride solution. Unfortunately, metal chloride molecules hydrolyze at higher concentrations, producing an acid chloride solution. The production of hydrochloric acid lowers the pH which holds the metal hydroxide molecules in solution. This aggravates the situation. The passive film does not form well at low pH. At this stage, a stable pit forms. Unfortunately, iron, the major component of stainless steel, hydrolyzes very easily, which explains its susceptibility to pitting attack. Growing pits lose some of the concentrated metal chloride molecules to the surroundings. As they diffuse away, the solution becomes less acidic and the solubility of the metal falls and precipitates as an oxyhydroxide a small distance from the mouth of the pit. This laboratory experiment demonstrates destruction of the passive layer as occurs during surgery. The plot indicates the reconstruction of the passive layer until full repassivation. When we compare the curves of stainless steel and titanium, we notice that the shape of the curves are similar, but that the time scales are quite different. Titanium repassivates much faster than chromium because it is much more efficient in obtaining its oxygen for the passive film directly from water molecules, whereas the chromium in steel prefers to use the rare dissolved oxygen molecules. At body temperature with a chloride concentration around an implant, the production of oxide from water is so efficient that corrosion can never produce enough ions to trigger a pitting situation. A defect in the passive film on titanium will always repassivate.